Okay, I'm now going to do a little calculation. A student carried out and planned and carried out an experiment to determine the enthalpy change of a reaction when magnesium metal reacts with acid. A student used this method. A measuring cylinder was used to transfer 50 centimetre cubed of aqueous solution of dilute acid into a glass beaker. A thermometer was placed in the beaker, 2.08 grams of magnesium metal powder added to the beaker, the mixture was stirred and the maximum temperature recorded. The student recorded a starting temperature of 23.9 and a maximum temperature of 61.2. It's a disguised, heavily disguised, calorimetry question. Where are your clues that it's calorimetry? Well, you've got a beaker. You've got something that's watery put into the beaker. 50 centimetres cubed of aqueous means it's water. Dilute means that there's a lot of water, a little bit of acid, but a lot of water. So I've got 50 centimetres cubed of mainly water in a glass beaker. I've got a thermometer in there and I've got the temperature change because I've got the starting temperature and the finishing temperature. The hard thing to work out is if I had delta H equals minus mc delta T, M is the mass of the water in the beaker, and it's given me centimetre cubed rather than grams. No worries, because for water, 1 centimetre cubed is 1 gram. It's got a property of density of 1. What that means is that 1 centimetre cubed is 1 gram of water, or 50 centimetre cubed of an aqueous solution, which is mainly water, is 50 grams. So now we're getting closer to the fact that we can probably do this. We've got a minus mass 50 grams of water in the beaker. Don't be confused by 2.08. We want the mass of the water in the beaker. 50 centimetre cubed is 50 grams. C, it's not giving us, which would have been a much bigger clue. It's very, very, very rare that they don't give you the specific heat capacity 4.18. I think I've actually cut it off from the bottom bit of the question by mistake. So that would give you a huge clue. If you see 4.18 in there, it's a calorimetry question. So I've got 4.18 and I've got the temperature change. So the temperature change is 61.2, take away 23.9, 37.3. Specific heat capacity is 4.18, that I think I've cut off the bottom of the question. Mass is the mass of water, 50 grams. It's not this mass of magnesium, the mass of the watery substance in the beaker. So now I can work out delta H minus 50 multiplied by 4.18 multiplied by 37.3 minus 7795.7 joules. To get joules up into kilojoules, like meters up into kilometers, or grams up into kilograms, from a small number, joules, up into our larger unit value of kilograms, I divide by 1,000, divide by 1,000, minus 7.796 kilojoules. That's how much heat is given out when I use 2.8 grams of magnesium. So it's a fair test to work out how much heat would be given out if I had a mole of magnesium. Not 2.08 grams, but a mole. So let's work out how many moles 2.08 grams is. If it's 1 mole, I've done it, I've got it. If it's less than a mole, I'm going to have to scale up. If it's more than a mole, scale down. Let's work out what 2.08 grams of magnesium is. Well, magnesium has got an MR of 24.3. So moles is mass divided by MR, 2.08 divided by 24.3. I've got 0.0856 moles of magnesium. I've got less than 1. So how do I know what to scale up by to find out how much heat would be given out if I had a whole 1 mole? Well, what I do is I take the fraction that I've got and I do 1 divided by it. It gives me the scale up factor. 1 divided by 0.0856 gives me a scale up factor of 0.68. Let me just break out for a minute for people that don't understand that. If I had 0.1 moles of magnesium, that's 1/10 of a mole. So if the amount of energy given out was for 0.1 moles of magnesium, it would be 1/10 of a mole. Now in your head you think 1/10 of a mole, 1 mole would be 10 times bigger. So I get the 10 times bigger by doing 1 divided by 0.1, which equals 10. So if you take the fraction of the mole that you've got and do 1 divided by it, it gives you a number that you have to multiply up by to imagine how much heat would be given out if you had 1 whole mole. So now I've multiplied 7.796 minus 7.796 multiplied by 11.68. That gives me 91.07 kilojoules, and that's how much heat would be given out for 1 whole mole of magnesium. Let's have a look at the next part of the question. Another student used the same method and obtained a value for the enthalpy reaction of something different, and the data book value is minus 310. How come they got a different value? The reason that this experiment goes wrong is because you get heat loss. If you get heat loss, then the numbers can be different from those expected. Or in this case, all of the magnesium had not reacted. I probably actually need to go back, sorry about this. I've not explained where the ethanol burner is. So I said this question was disguised. Magnesium metal is the ethanol burner, except that rather than it being underneath the beaker, magnesium is reacted with some dilute acid in the beaker. It reacts and makes heat when you put it in. So magnesium is, in effect, my ethanol burner, my fuel source, but instead of it going underneath the beaker, it's going in. So, and reacting in. That's a subtle change, and that's why it's a bit of a tricky question. I've chosen it. So why might the experimental value be different than a data book value is that sometimes heat loss, you've got heat loss going on, you should really insulate the beaker or put a lid on there. Or sometimes not all of the magnesium may have reacted, but your best answer, your easiest answer is heat loss. Now, when I put the magnesium in, something happens. This is the temperature of the water. First of all, it's not changing, not changing, not changing at all. And then on, usually about 4 minutes, we add the magnesium in. And then all of a sudden, the temperature goes up, 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 and starts creeping up, and then starts cooling down. Like that. Now, you get a curve like that because the glass thermometer isn't very good at measuring temperature quickly. It goes up slowly and then starts to cool down as the mixture starts to cool down. If the thermometer had been better and it had been a digital thermometer, it actually, when I added the magnesium here on time number 4, it would have shot right up. Yeah. But a thermometer is glass with some mercury inside it, and the mercury heats up, it expands, it creeps up slowly. So a thermometer takes a little bit of while to get to temperature, and then it cools down. If it had measured the temperature straight away like a digital thermometer does, it would have just gone straight up and then straight back down. So we need to measure this change and try and imagine what would happen if we had a better thermometer. So you draw a line to 4 minutes. You draw a line back from where it starts going down back to 4 minutes. This line here on the bottom x-axis is time and up the side is temperature. This is 4 minutes here. I've not taken a temperature reading at 4 minutes because I was busy adding my magnesium in, but at 4 minutes, this is what it would have been if a backtrack called extrapolation back along this line of straight points here. It would be here, and the temperature change would have gone along and then shot straight up and then straight down if my thermometer wasn't a poor thermometer, if it was a better quality thermometer or a digital thermometer. So my temperature change is from here, before I added the magnesium, and I've extrapolated, worked it back to 4 minutes when I added the magnesium, and I'm going to measure this temperature here from a graph. So, suggest how the student's method and the analysis of the results could be improved in order to determine a more accurate value of the enthalpy reaction. Justify your suggestions. Do not refer to the precision of the measuring equipment. Do not change the amounts of the concentration of the chemicals. Insulate the beaker. We've already said there might be some heat loss. Record the temperature for 3 minutes and then add the magnesium on 4 minutes. Okay. Draw a line across Before you've added the magnesium, draw a line backwards called extrapolation back to 4 minutes, and then measure the temperature change from here, reading off the graph, to here, reading off the graph, and measure the temperature change here to put into your calculation.